So now that we finished arrays, let's go back. Let's go to linear search. One moment. There you go. So, covering linear search. I hope everyone's here. I'll give a bit. Now, here's a thought experiment. Suppose I hand you a stack of 50 index cards. Each card has a number written on it. They're in random order. I ask you, is the number 22 in here somewhere? In this big stack of index cards with numbers written on it, is the number 22 written somewhere? Now, answer in chat. How would you find out? Just think about it for a second. How would you actually do this with cards? Like the process, what would you do? Would you read the cards? Mm-hmm. Check each cards. Anyone else? Mm-hmm. So yeah, you're checking each card, or maybe you're gonna lay it on a flat surface and find the 22 card. So what you're doing here is the right answer. It's the obvious answer. It's you're flipping through them one by one. So here. Now, what if 22 is the third card you flip? Right? Because you're sorting through the cards one by one and then you find 22 at the third card. Right? You stop. No reason to keep flipping. Because there's already 22, so you stop there. Now, what if 22 isn't in the stack of cards that I gave you? So, what are you going to do? Like, if 22 isn't in the cards I gave you at all. Using the same concept, we're going to keep flipping through every card. Because it's not in the stack, it's not in the third one. I mean, if it was in the third one, you have it. But what if it wasn't? So now that it isn't, what do? You just keep on flipping every card because, well, you're gonna have to find it eventually. And you still flip every card, so on, so forth, even if 22 was the very last card. If it's the third, you stop. If it's the fifth one and it's not there, you keep going. If it's the very last card, you keep going until you hit the very last one. Bad luck, right? It sucks. But you still find it eventually, right? And that's what matters, you found it. So, what I just described, that's the concept of linear search. The linear part is because you process the list in a line start to end. So, one item at a time. Even if you lay it flat on the surface, you're looking at it one item at a time. No tricks, no shortcuts, it's genuine, honest work. And here's the beautiful thing linear search works on anything sorted, unsorted, integers, strings, whatever. No assumptions, it's just gonna walk through and check. Now, before we write code, let's describe it in plain English. This is how every algorithm starts words first and then code. Here. So let's look at some pseudocode. On the screen, you can see some as an example, and I'm going to be reading it aloud slowly while you watch. So here's the line. For each index I from 0 to array.length minus 1, right? This is our loop. Walking through every position in the array because we're going through it one step at a time from 0 by the array length. So 1, array length minus 1, array length minus 1. So think of an array length of 6, 6, 5, 4, 3, 2, 1. And that's what you're doing because you're indexing it all the way to 0. So here. Now, if the array equals target, that's the check. If Ri is already the equivalent of 0, that's already the target. Because we've somehow, in that list, found what we wanted to go. Oh, yeah.
Are you sharing your screen?
Oh, am I not sharing my screen?
Yeah, no, you're not.
Oh man. It's okay. Thanks for letting me know. Thought I had it shared. It's okay, you guys didn't miss much. So you only missed one slide, but the slide here doesn't really matter naman because it's the same question I asked you about the cards. This one only requires visual thinking naman. Here, here. Okay. So moving on, because Butapay pointed that out. This one you don't really have to look at the screen here. It's the question that matters. Now, let's move on. Here is the pseudocode for example. I'll start from the top. For each index I from 0 to array.length minus 1, right? For each index from 0 to array.length minus 1. Array.length is going to subtract it from the length of the array minus 1, and we're going to start from index 0. Therefore, we're going to keep going until we find the number we want, right? Because I is the number we want. And that's what we're looking for. If our I equals target, return I. So if we found it here, we stop here. And the loop ends once the target is absent. So if I is gone, because the target is gone, index I, that's it. It's absent. So in simpler terms, that's the check. Return I. We found it. Give it back to the position. Stop here. Return -1. We got through the whole loop without finding it. Signal, aka not found. So that's what happens. If the loop finds it and it's not found, it does signal that it's not found. So 4 lines, that's the entire algorithm in plain English. This is already linear search. This is the base definition and it's as simple as it gets. Now, you might be thinking, why do we return -1 when we do not find the target? But D0, why not some other number? You guys want to try answering that question? Why do we return -1 when we don't find the target? There's other numbers. Why not 0? Why not some other number? Exactly. Because 0 is a valid index and -1 is not a valid index. Since 0 is a real index, the first element, if we returned 0 for not found, we couldn't distinguish found at position 0 from not found at all. -1 is a value that can never be a valid index, so it's unambiguous. So basically, we're abusing that whole never valid index thing by going into the negatives. And look at the return I, right? Return I that we have inside of the loop. The moment we find a match, we leave. Why? Because there's no point in checking the rest of the cards once you found the one you want. On a 1 million item array, that's an enormous amount of saving. Because let's say that in a 1 million item array, you only need number 7. Therefore, you're going 1, 2, 3, 4, 5, 6, 7. So, go 7 times, diba? Why would I have to go count the 1 million before I finally get that return? And that's the magic of linear search. Now, the C#. Watch how almost every line of pseudocode maps to one line of code. And that's what good pseudocode does for you. So, in actual implementation, here's real C# code. Let me read it aloud line by line, following what's along the screen. So, line 1. Comments, purpose. So here, line 1, comments. Its purpose, find the first index where array, ri, equals target, returns the index, or -1 if absent. Okay? The purpose is to find the first index where array equals target, returns the index, or -1 if absent. Always write comments like this when you're learning, because when you're revisiting a code base, future you is going to thank you. And it's going to really build the foundation for understanding code so you can start, doing this from scratch. It's not something you need to understand perfectly, but it's like a muscle memory. Oh, I've written this before. So you write it like this. That's how I program personally. I don't have the brain to store a billion concepts in my head, but I have the muscle in my fingers and a bit of my subconscious brain to understand this pattern that I'm seeing. So here, walk every index, check if this is the one. If yes, stop and report. Return is loop through all. nothing matched. And that's how simple it is. This line of code walks through every index. We've covered this before as a loop, right? r.length I++, and it's going to check if this is the one, if this is the array that we're looking for, right? Is this the one? If yes, stop and report back, which is return I. You're returning the report. If it's already looped through everything, return -1, meaning nothing matched what you found. So, going back, now we explain line 1. Let's go to line 2, the method signature. Line 2 is the method signature over here, where public static int, right, over here, is public static int linear search, open paren, int square bracket array int target, close parenthesis. Public means anyone can call it, right? So when we say public, anyone can call for this array in your line of code. That means you can use this array anywhere. So static means you don't need to make a new object first. Just call it. Int is the return type. We're returning an integer index. Okay? So this is the type that we're returning, int. So we want to return integer. Public is accessible and return int, right? Okay, I hope I'm making sense here, because conventions are something in ISP or GG1 and ISP or GG2, but it's just good to cover all over again. So yun. Static means, again, that you don't need to make a new object first, and you just simply need to call it. So that's it. It's the return type, and we're returning an integer index, public static int. That's it. Inside the curly braces, for open parenthesis, int I equals 0, I less than array.length, I++, close parenthesis, the standard pattern, right? That's what we saw, the standard pattern. It's on slide 7 that we saw earlier. Now, inside the for loop, if open parentheses, int I equals 0, I less than array.length, I++, close parentheses, the standard pattern, again, yeah, the standard pattern again. Sorry, I explained it again. Yeah, my bad. We're talking about the inside the for loop. We're talking about this as a whole. I was reading it line by line. Okay. So here, inside the for loop, if open parentheses, okay, ri equals here, equals this time. Target, close parentheses, open brace, return I, semicolon, close brace. That's a mouthful again. If r allowed, that's if r at I equals target return I, right? And after the for loop is return -1, which is semicolon. If we got here, we made it through the whole loop without finding the target. So we return the sentinel, which is -1, and it's like, well, nothing's here. That's it, basically. In simpler words, I already put in the comment, walk every index, check if it's the one, stop and report, loop through it all, nothing matched. I just want to complicate it a bit because we have to understand why these mean this. So, what's the difference between equals and equals in C#? Why do you use each one? Do you guys know what the difference of equals and equals is? Kite a yes or no is okay. If yes, answer why after. 5, 4, 3, 2, 1. That's okay. Because single equals, note this down, single equals is an assignment. You're putting a value into a variable. So x equal 5 means set x to 5. Okay? Again, single equals is an assignment. So if if you want to say x equal 1, you're assigning 1 to x. Gets? So here, double equals in comparison is you're asking a yes or no question, okay? So it's not anything that's like, oh, I'm assigning it twice. No, you're asking it a yes or no question, a boolean essentially. So x equals 5 means this in words. Is x equal to 5? So if you write if x equal 5, with single equals, you've simply just assigned 5 to x, and the condition becomes, is 5 truthy? Subtle and terrible bug, right? And that's what you don't want. So a common issue that some people get in C# is the half-open interval notation. 0 length is everywhere. So square bracket means inclusive, parenthesis means exclusive. So square bracket zero length means from zero up to, but not including length. You have to get used to these notations of what these brackets and parentheses mean as well. So if it still confuses you, I suggest you read this in your spare time and understand why we're writing it this way. So here's a live demo. This live demo is how we get to showcase the array on screen, right? This is a linear search array on screen. 14, 7, 3, 22, 9, 18. And we're searching for the number 22. There's a step button and a run button and a reset button. I'm going to use a step so we pace ourselves. Now, before I press anything, predict. How many comparisons do you think this will take to find 22? Just write your answer. Any number is fine. How many comparisons do you think? Mm-hmm. So it seems like consensus is 4. And that's a good guess. So let's see if you're right. So step 1 is over here. Step 1, I equals 0, R0 is 14. Is 14 equal to 22? Guys, is 14 equal to 22? No, Diva, it's not equal to 22. So what happens next? The line of code goes through the next sequence. Now, step 2, I equals 1, R1 is 7, right? So is 7 equal to 22? No, again, we move on. Now, step 3, I equals 2, array 2 is 3, right? That's 3. Is 3 equal to 22? No, we're gonna move on because 3 is not equal to 22. So, next step. Step 4, I equals 3, array 3 is 22. That's a match. Return 3. It's a bit of a tongue twister on my end, my bad. I need to drink water. But yun na nga. That's it. It's just a step-by-step process until it checks and compares every number. Oh, it's not 14. Oh, it's not 7. Well, it's not 3. Oh, there, I found it. It's 22. It's over here. And that's how it works. That's it. That's it. So, yun. We're looking at the counter, 4 comparisons in total. So tama naman, whoever answered 4 kanina, you're right. That number is going to matter in 2 slides on why we chose 4 as well. So, yeah, we can reset and run a different target. Here's how it looks like in an actual computer perspective. Matic, comparisons 4, I equals 3, return 3 since I is 3 in index 3. That's it. So you just watched it. Now, let's write down how it happened. That's called tracing, and it's a skill that turns confusion into mastery. Now, this one you won't find in the curriculum, but I think it's necessary to know because it's going to give you an easier time towards understanding linear search. Tracing is the single most useful technique I can teach you this semester. It's how you understand what code actually does versus what you think it does. When code confuses you, you trace it. Always. Okay? So here's a trace table. This is the found case, right? On the left side, we're tracing linear search on our array, looking for 22. Each row is one iteration of the loop. So this is loop 1, 2, 3, 4. Watch the columns, okay? Iteration number, what I is, what array at I is, the comparison, and what action we took. So here's how it looks like. This is a trace table. You actually understand how your program works once you make this trace table because you understand each data and understand why is it continuing. Continue. It's all continuing because these checks are false until it's true, then returns a 3. And that's how you make a simple trace table, right? Because iteration 1 is I0, R at 0. 14 is 14 equal to 4 is 14 equal to 22? No, action continue. Iteration 2, 7 is equal to 22? No, continue. Iteration 3, 3 is equal to 22? No, continue. Iteration 4, right? 22 is equal to 22. Yes, Action return 3. So that's 4 rows, 4 iterations. The function returns 3. Whenever a piece of code confuses you, you just write this table out by hand. Even an iPad. I have a blueprint. I have an iPad I use for making blueprints, and I always make tables like this when I want to know any back-end processes and how they function. This can get as complicated and as simple as you want it to be, but it's very useful because the bug is always in a row you didn't write. Because notice how I was able to explain all this, right? Now, let's look at the right side. Same array, but we're searching for 99. But you notice how 99 isn't contained within the array. It's outside of the array. Now watch what happens. We get 6 iterations total because this is long as 6. 1, 2, 3, 4, 5, 6. So that's 6 total iterations. Every single one returns a nope, not equal to 99 after the loop ends. And we fall through and return -1. Now, here's the important number. 6 elements, right? So because we have 6 elements, that's 6 comparisons. The size of the array dictates how much work we did. Keep that in your head, because in 2 slides, we're going to give this concept a name. Now, question for everyone again. Imagine the array has 1 million numbers and the target is not there. How many comparisons does linear search do? Again, if an array has 1 million numbers and the target's not there, how many comparisons does linear search do? Okay, I mean, that's a good guess. Anyone else? Okay, you guys are right. I was messing with you all again. So yun, 1 million, right? You guys understand the concept perfectly. If you answered 1 million, 100%, you're fine with the concept. You understand the trace table and you understand how linear searches work. So, 1 million comparisons, that's a lot of work, and we need to fix that, but not with linear search. We're going to use a smarter algorithm we'll meet later, and that's binary search, but we're staying in linear for now. So now we can talk about how much work linear search does in general. So, how much work does it do? It depends, really. It truly depends. Computer scientists break this into 3 cases. Let me walk you through each of them. So, best case card. The best case is the target is at index 0, the very first card. Only 1 comparison is done. So we say this as O of 1, constant time. You got lucky, and that's the best you can possibly do because can it get any faster than landing it on the first try? Nope, that's the best case. Therefore, you're at an O of 1. Now, average case, on the other hand, assume the target is equally likely to be anywhere on the array. On average, you'll find about halfway through, right? So you're gonna find it halfway and be like, well, there it was, there it was in the array, there was the word in the dictionary. So roughly, n divided by 2, right? Because you're finding it halfway through. So n divided by 2 comparisons, where n is the size of the array. So 6 divided by 2. So now you're doing 3. And that's all the comparisons you're going to do on one side. And that's O of n over here in the average case. And the worst case, right? Worst case, O of n once more. The target is at the very last position. Or it's not in the array at all. Then you check every single element, right? N comparisons. We say this as O of n. Linear time. We'll define this notation properly in a couple of slides. Now, here's a real question. Why do we usually report the worst case when the average case is more typical? I'll give 10 seconds for this. You can answer a simple answer. It's okay. Nothing complicated. It's fine. Again, why do we report the worst case when the average case is the typical case? Five. That's okay. That's okay. Kasi, here. Imagine your boss asks you, guys, how long will this take? They want a guarantee, diba? Not hope. The best case is a hope. Because you want to answer your boss, you can't tell your boss, Di ko po alam, sir. You have to tell them an answer because obviously that's what they hired you for. So you have to provide them like actual, an actual sure hope thing. Like, a good shot, an educational guess, diba? Sometimes you're lucky. The worst case is a guarantee, diba? This algorithm will never do more than n comparisons, and that's what we report because that's what you can plan around. So you can always plan around the amount of comparisons you're gonna do. And bonus question: on a million item array, the average case is half a million. The worst is a million. Is there really any practical difference between these two numbers? Again, on a million item array, the average case is half a million, diba? The worst is a million. Is there a difference between these two? If we were to do half a million versus a million. Because average, million. Average, half a million. Worse, a million. Can you guys tell me what the practical difference is? Like, argue with me here. What do you think? Okay. On a million item array, the average case, diba? The average result once you run this code is gonna be half a million when you do a linear search. That's the average case, diba? And the worst case scenario is a million searches compared to the half a million searches. Is there really any practical difference between a million and half a million in this scenario? Okay, Matt. Tama ka. Half. Tama ka. So, you're not wrong. 500,000 versus 1 million, it's real. Diba? It's real. But, and this is the key, the shape is the same. Both scale linearly with the size of the array. No matter what, they're scaling linearly. It's getting harder as it scales. So both feel slow at the end of the day. And Big O is going to throw it away, the divided by 2, because the shape is what matters. You want to look at the shape of how your data looks. And that's the thing. No matter what, half a million or a million, it's still slow. It's still searching linearly. Sure, a million takes more time, but it's still searching linearly. Now, the right answer here is actually they're both terrible. That's right. Even though you do get the average case, that's still bad. Because both are linear in n, the constant factor, right? Both are linear in n. The constant factor, half versus full, doesn't change the fundamental shape. And that's exactly why Big O drops constants. The shape is what actually matters. So here's one more linear search slide. Then we're gonna break. Then we have a name of this growth and pattern properly shortly. So here's a beautiful thing about the linear search pattern. Once you can write it, you can write a dozen variations just by tweaking the loop body. Each of these on a screen is a real interview question. Okay, you're gonna get this when you're actually in the industry. So variation A, count occurrences. Instead of returning the first index, count how many times, these are variances of linear searches, count how many times the target appears, start counter at 0, increment it every time you see a match, return the counter at the end, and that's a count occurrence. Variation B, for example, is find the maximum. Start by assuming the first element is the max, right? So we're going to start from 100. Walk through the rest every time you see something bigger, then update your max. Pretty interesting, right? So every time your function returns a big number, that's going to be your next max. That's going to be your next max, 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 max. Variation C is find the last index. Instead of doing the first index, don't return early. Keep updating a variable every time you see a match. Whatever the variable lacks, whatever the variable holds at the end, is the last index. And variation D is find all the indices. And what we're doing in variation D is collecting every match onto a list, and then we return the list. So we're basically collecting the whole of array.length, and then we're returning that array.length in a list, and we're using it from then on because you turned it into sorted data. All of this turns it into sorted data. So here's a C# example. Look at this code. It's example written for variation A, count occurrences, right? One loop, one comparison per iteration. It returns a count instead of an index. So here's the key insight, and I want you to write this down, okay? All four of these variations that I just talked about are still O of n. The shape of the loop determines the runtime. It's not what's inside of the code, but how the shape looks like, right? Whether you return early, count, find max, or collect, it's still one pass through the array. So it's still a linear time. No matter what, as long as it's one pass through the array, you're going through it linearly. It's the way. Oh my god. So yun. Alright, that's linear search. Time to give everyone another break. So sana nagets mo naman, and as usual, I'm dropping another exam, so kindly do send it to me, and I'll be looking for those who sent me their exams. I'll be able to assess it and know your weak points, so I may give you learning materials for it, okay? So please do send me your scores, no shame, it's fine. We're all here to learn. So yun na nga. Let's have a break. It says 10 minutes on the board, but I want to eat my food. My mom made food. She made chicken kasi tsaka gusto ko na kumain. So let's have a 30-minute break, okay? So let's be back 6:30, and when we come back, we're gonna be talking about the growth pattern that we've been dancing around. Big O. Okay, break time. I'll be back. You guys don't have to leave this call. This is the call na talaga. I'm dropping the assignment in the Distalgo chat.